Okay. So now I would like to invite our next speaker, Dr. Srijani Anurag Prasad. She is working at Department of Mathematics and Statistics at Indian Institute of Technology, Tirupati. Our title of the talk is Edelstein Hidden Variable Fractal Interpolation, Construction, Smoothness, and Dimension. So over to you, ma'am.
Thank you, Megha. So, good morning and good afternoon. So, I would like to thank the organizers for this opportunity to present this work. This is a joint work with my PhD student, Ms. Aishwarya. So, in this presentation, I'll give a brief construction of Edelstein with hidden variable fractal interpolation and show the results on the smoothness and dimension. So, this is the one second. This is the outline of my talk. I'll give a motivation for the construction and some few results required for the same, and then I'll describe the construction method, and finally the results on smoothness and box counting dimension. So in general, we know that given any interpolation data, Barnsley gave the method of fractal interpolation method, and it is a modern approach to model the irregular and nonlinear data sets. The fractal interpolation function inherently captured the self-similarity and non-linearity. And this construction, it was based on the iterated function system consisting of Banach contractions. And over time, and of course, the graph of an FIF, it is basically coinciding with a attractor of a graph of an FIF coincides with the attractor of an IFS. So over time, there have been a lot of important generalizations like multivariate fractal interpolation functions, superfractal interpolation functions, and then nonlinear fractal functions via the Rakkoch, Makotsky, and Edelstein contractions. And then we also have histopolating fractal functions for histogram type data. Now, the classical hidden variable are constructed using the Banach contraction, which requires a uniform condition. So this actually limits or the flexibility of the model, and some class of self-similar functions are not captured within this classical hidden variable fractal interpolation functions. So to overcome this limitation, we replace with the Edelstein contraction so that it has non-uniform contraction factor, and that is a broader and more flexible extension of a hidden variable fractal interpolation function. So here a few results which are required. So what is an Edelstein contraction? So for x and y not equal, mu, the function is said to be Edelstein contraction if the distance between the image, h is said to be Edelstein contraction if the distance between h of x and h of y is strictly less than the distance between x and y. If this happens, then we say that h is an Edelstein contraction. So they are strictly weaker than Banach contractions, and Banach contractions are sitting inside our the space of Edelstein contractions. On compact spaces, the Edelstein contraction map ensures the existence of fixed point. Now, to construct any fractal interpolation function, it basically relies on the iterated function system. So, and what is an iterated function system? It is a complete metric space together with a finite set of contractions on that metric space. And when we have an iterated function system with contraction map, it is already proved that it has a unique non-empty compact set satisfying its self-referential. That is to say that the set is written the union of its subset, and each subset is scaled version of itself. So such a set we call it to be an attractor. And fractal interpolation functions, they arise when graph of the function is an attractor. So Now we will see the construction of the Edelstein hidden variable fractal interpolation function. Given data in R2 where my independent variables are tj's and my j's are functions f of tj, my tj's are taken to be in increasing order. So to the given data, we augment the hidden variable wj's, and that introduce the additional degrees of freedom, and they are independent real parameters. So we have the augmented data, or sometimes we call it generalized data. Now LJs are functions, or they are contractive homeomorphism from the larger interval. So if I denote the larger interval T0 Tn by I, then the subintervals, say Tj minus 1 Tj, they are denoted by Ij. Then LJs are contractive homeomorphism from the larger interval to each subinterval such that the endpoints of the bigger interval I is mapped onto the endpoints of Ij. Next we choose we take 4 real valued Lipschitz function, and these real valued functions are chosen such that the sum of the supremum norm of Bj and Dj, they are less than or equal to 1, and the sum of the supremum norms of Cj and Ej, they are taken to be less than 1. Now we take 2 Edelstein contractions on R, and then with these we go to define a few matrices. So they are denoted by dj of t, and here we have sj v comma w. So this consists of this matrix, or is an array. It is having the Edelstein contractions on R. So by this way my capital Sj function becomes Edelstein contraction on R2 if I choose Manhattan metric. And the last array or matrix Qj of t has 2 functions Pj and Qj of t. These are real valued Lipschitz function, and the conditions to choose this is if I define the function capital Fj from the space I cross R2 to R2 as given by the equation number 3, like the dj matrix dj of t into sj plus qj of t. If I take this as my fj maps, in this the real valued functions pj and qj, they are chosen such that these endpoint, like my fj at the endpoint t0 v0 w0, it is mapped on to the value of vj minus 1 wj minus 1, and my endpoint fj tn vn wn, it is mapped to vj wj. So as I said, the matrix capital Sj, they are Edelstein with respect to the Manhattan metric, and using that we prove that the capital Fj is also Edelstein contractions in Manhattan metric. Now we go to define the iterated function systems. So I take my Gj, which are going from, so my K is any compact set on R2 which contains all the points Vj, Wj's, and as I do iteration, all the points are also inside the same compact sets. So with this definition of little Gj on the space I cross k, so I is a compact interval, k is a compact set, my I cross k is compact. So we define on that compact metric space the function Gj. Now on the space of continuous functions defined on the interval I, we define the Reed-Bashkevich operator given by this equation RH of t in terms of, or using my functions capital Fj of Lj inverse of t and h of Lj inverse of t. Then we can see that my Reed-Bashkevich operator is a contraction and it has a fixed point f. This fixed point interpolates the given generalized data. And when I write this, sorry, where the graph of this fixed point, it is the attractor of the IFSI. So writing this fixed point in component wise, the first component, it passes through the given data set, and that is called as the Edelstein hidden variable fractal interpolation function associated with the given data set. So here we have taken some examples, random data set, and to that data set we have augmented our WJs. So we have taken 0, 0, half, 1 by 4, 5 by 24, and 1 by 8, 185 by 288. The third point is 2 by 3, 9 by 16, 241 by 288, and the last point as 111. Now, my L1s are constructed satisfying the equation that using this equation Lj of x, it should be Lj of t, that's a typo, Lj of t. And in the first two rows, I have taken S1 as V by 3, S2 of V as V square by 2, and S3 of V 2 by 3V. And R1, R2, R3 as taken as. So these two, the first two rows gives me an iterated function system with Edelstein contraction. So with this, we have constructed the EHFIF, which is given here, that is my blue curve G1. So G1 is the, H1. H1 blue curve is the Edelstein hidden variable fractal interpolation function corresponding to the data set that we have given here, V star. Now for the same data set, we also took these S1 prime, S2 prime, S3 prime, and these are nothing but giving me Banach contraction. So for these Banach contraction, if I am just using, so as I said, Banach contraction is a subset. Those functions lie inside the space of Edelstein contraction. I can go to use them with the same. So I get a HVFIF corresponding to the same data set, and that is given by my red curve. So in this, I have gone to show both the Banach contraction iterated function system, which is giving me the hidden variable fractal interpolation function, and the Edelstein hidden variable fractal interpolation function for the same data. Now we will just go to see some few results for smoothness and box counting dimension. So see the smoothness result. For simplicity, I am taking the closed unit interval. So by the construction, using this Reed-Bachsterovic operator, my fixed point F1 and F2, which are the components of my fixed point F, they satisfy these self-referential equations. Now, these are some notation to help me derive the smoothness result. So my theta j is just maximum over all modulus bj of t and cj of t, which is occurring in the function f1, and my theta j dash is the maximum over dj and ej, which is occurring in the function f2. And denoting the minimum of all intervals by I min and maximum of all interval length by I max. So when my theta j and theta j dash, when they satisfy this inequality, that twice the maximum of theta j and theta j dash divided by mod ij, if it is strictly bounded by inverse of I max, then the Edelstein hidden variable fractal interpolation function, it belongs to Lipschitz class with the exponent alpha and Lipschitz constant k. This gives the smoothness of F1. And similarly, a result also holds for the F2 function, and that F2 with the same condition, it shows that it is in the Lipschitz class of beta, where these alphas and betas are depending on these theta j's, alpha j's, I'm sorry, bj's, cj's, dj's, ej's, as well as on the pj function and qj function. So depending on these, alpha depends on these quantity. And since it was a very large quantity, I did not go to write. I have just written the result. And using this smoothness result, we see that the Edelstein, the graph of the Edelstein function is bounded above by the upper box bound for the box counting dimension is given by 2 minus alpha, and the alpha in general mostly lies between 1 and 2. So we have here a number lying again between 1 and 2. Yeah, so these are some very few references. I did not include all the reference. But the paper is already published very recently in 2025. I'm sorry, 2026.
Okay.
Thank you.
Thank you, ma'am. Thank you for the nice presentation. So, of course, we'll have for some questions from the audience if they have. So, if there is no question, so let us thank the speaker and we'll start in 5 minutes for the next talk. Thank you. Thank you again.
Thank you.